Section 2.1 is called Tangent Lines and Velocity. And the first thing we're going to talk about is we're going to talk about what in the world a tangent line is. But before we do that, because that's part of the title, we're going to actually look at a secant line. Now, you have heard these words before. We've talked about them in class before as well. When we talked about them in class, we referenced tangent lines and secant lines in terms of to what shape is the first shape you'd heard these referred to. Circles. Yeah, so you usually first encounter these in a geometry class when you're working with circles. And we've encountered them in this class before as well when we talked about them back in section or chapter 1. I think it was 1.1. And we talked about the fact that a secant line does what? Do you remember? Yeah, it cuts through the graph. So it actually cuts through, generally speaking, it's a line through 2 points on your shape. And in geometry, it's 2 points on a circle. In calculus, it's 2 points on any particular graph. And in particular, we're going to do graphs of functions. Now, a tangent line, how does that differ? What's different about that than the secant line?
It only touches it.
Yeah, it only touches it at one point. Now, it's only touching it at one point nearby, so the graph that I'm going to draw really looks like it only touches it at one point. If this graph were drawn a little bit differently, it could actually cross over it twice. By default, because the graph goes out far enough and it does something else, like maybe it curves back up or something like that. When we encounter that, I'll show you what I mean. But what we're going to be working with in this section is finding the slope of either of these lines. And in particular, the slope of the tangent line is what we're going to be looking at. So if we talk about the secant line, and we talk about different points on the secant line, namely, let's say that this point is A, which means that the y value is f of A. And this point over here is A plus H. That is, it's wherever I was at A before, and then it's more, right? It's a little bit different from what A was. Then this y value we call f of A plus H. Okay, it's just the y value at the value, whatever the x value was. So we have these two lines. We have the line, or 2 points, excuse me, the point with A and A plus f of A. And then we have the point with A plus H and the y value f of A plus H. It's just a pair of points. Okay, so when we do these specifically, we'll have them be, they won't look quite so generic, but this is generically. So the way we find the slope of a line is we take the y values and we subtract them on the numerator. And we take the x values and we subtract them in the denominator. So the two y values from these particular points are f of A plus H and f of A. And the two x values are A plus H and A. So these are y values here on top, like y1 and y2. These are x values like x1 and x2. Now, these two y values, I can't actually simplify how that's written, but the two x values don't have a function notation with them. It's just A plus H and A, which means I can simplify that, right? The A and the negative A here at the end, those reduce. They disappear to 0. And all I'm left with in the denominator is H. So all of that actually simplifies to finding the difference in the y values. This is what this is. This is the difference in the y values. And H is the difference in the x values. And if you look back up on our picture, that's exactly what it is. This distance right here is H. And that's the whole point. I separated them by some value H. In general, H needs to be, it's going to be something very close to itself. I mean, you're not going to get two values that are this spread apart. But in terms of the picture, it's easier to draw if I draw them spread apart a little bit. All right, so the next one right here is a definition. And when we get to exam 2, I know we haven't even done exam 1 yet, but when we do get to exam 2, this is one of those things where you're going to memorize it for me as well. This is the definition of the slope of the tangent line. So the slope, m tangent, of the tangent line to the graph y equals f of x at the x value of A is given by the limit as h goes to 0 of f of A plus h minus f of A over h. This part is exactly what we did on the page before. This piece is telling you that the h value, that is the distance between the two x values, is getting very, very small. Those two x values are getting very, very close together. I'm going to draw you a picture of what's going on here after you guys have a chance to write that down. Now the image I'm going to draw, you are welcome to draw it on top of the graphs you already did above, where you had the secant graph. But imagine you had that graph, which is an upside down parabola, and you wanted to find the slope at this particular tangent point. So you wanted to find the slope of this line. That's our goal, is to find that particular line and the slope of that line. In essence, what this definition is doing is saying we could find the slope of this line. It's a secant line. And that'd be pretty easy to find. I can calculate whatever this point is. It can be found because I've got an equation, y equals f of x. So if I pick the x value, I can find the y value. I can calculate that slope. No problem. That's algebra. You guys know how to do that. But what we're going to do is we're going to let those 2 points get very close together. Now the point that I'm caring about is this one, so I'm not going to let that one move. What I'm instead going to do is I'm going to let the other point get closer to the value I wanted. So imagine now taking and looking at this point. It's closer than the other one was. Oops. And now you find the slope of that line. Well, that's closer to the tangent line I want. And the reason it's closer is because the point's closer than the other point was. So if we then take that little point and get it a little bit closer, and maybe now it's here.
So we go from like a secant line to a tangent line?
Exactly. So these lines are getting closer and closer. As those 2 points, as the second point over here that's to the right gets closer and closer to the point on the left, the line that you're creating between the points is getting closer and closer to the tangent line that you're looking for anyway.
Because that's like our length of h, just getting closer and closer.
Exactly, because the distance between the a value and the a plus h value, with h getting infinitely small, getting very, very small, is going to 0. The 2 points are getting closer together. The difference between them is going to 0. And that, whoops, is exactly what this limit notation is saying we're doing. This notation right here, oh, good grief. There we go. This limit notation right here is saying the points are getting close together. That's what that h going to 0 means. Since that h is going to 0, it's saying that the 2 x values are getting very, very close. And correspondingly, if the x values are getting close, so are the y values. Maybe close faster and maybe not as fast depending on the function you're working with, but they're also getting closer together as you move along the graph. Now, that's conceptually what's happening here. Now we're going to look at how that works out algebraically. Ready to take a look?
Yeah.
Okay. Here's what we're going to work on. It wants us to find the equation of the tangent line. So in order to find an equation of a line, what do we need to have? Points. So we could have like 2 sets of points. That'd be one way to do it. What else could we have to find an equation of a line?
Points for slope?
We could have one set of points, or 1 point rather, that was my fault, 1 point and 1 slope. That'd be another way to do it. And there's another way, there's a third option. Maybe just a more specific way of saying what you just did, Luke.
Slope and a y-intercept?
You could have a slope and a y-intercept, the specific point that's the y-intercept. So we're going to do it from that perspective. We're going to look for a point, and we'll use just a general point, and we need a slope. So we're actually trying to, our goal here is to be able to take the formula for a point slope formula for a line, which is y minus y1 equals m times x minus x1, and to plug in essence, the general point here, x1, y1, and the slope. Okay, so does everybody understand what our goal is at the end? Our goal is to have the equation of a line, and in order to have an equation of a line, I need a point, and I need a y, and I need a slope. All right. The way that I get the slope is by doing this process. Okay, that is the definition that I just did before, this limiting process. Now, it actually tells me the x value right here, it's a, equals 1. So I actually know this value over here already, x is 1. And I could find out very quickly what the y value is when x is equal to 1. How'd I do that? I'd plug it into my formula. So if I plug in 1 for x into 6 minus x squared, what's y going to be? Right. Positive 5, though, I think. Right? Yeah, because the 6, yeah, it's switched. All right, so the y value is going to be 5. So I actually know the y1 and the x1 value. M is the only thing I have to find, really. So this is not calculus so far, but we're about to do the calculus part of it. All right, the calculus part says that in order to find the slope, which is what I need to take the limit as h goes to 0 of some stuff. In particular, that stuff's going to have h in the denominator. Okay, everybody good so far? Now the numerator is supposed to look like this, f of a plus h minus f of a. But what is our a? It's 1. So for ours, it's going to look like f of 1 plus h minus f of 1. Because it's supposed to be a plus h minus f of a. Okay, so all I did so far is I replaced x, or not x, but a actually in our formula, the value a with the number 1. Everybody good? Okay. Now you know what f of 1 is. We actually already calculated it. What is f of 1? It was 5. So let's take our next line of our work. Notice we're rewriting that limit h goes to 0 just like we did with limits in the last chapter until we actually plug in 0 for h. What's wrong with plugging in 0 for h right now?
It'd be undefined.
It'd be undefined because I put a 0 in the denominator. So my goal as I'm working on this is somehow that h has to go away. Otherwise, I'm never going to be able to plug in h as 0. Right? Okay, so somehow in all the midst of the work I'm doing, this h in the denominator is going to cancel with something in the numerator, like in an appropriate way, not just because I marked it out. It's really going to cancel. Okay? All right, so how in the world do I find f of 1 plus h? That's the part here that's a little bit harder to conceptually put in there than the other piece. What do I do to find f of 1 plus h? Do you remember from algebra how that works?
Plug it into the x value.
Right. So where I have an x in my formula, 6 minus x squared, I'm going to plug in for that x value 1 plus h. So this is going to look like 6 minus 1 plus h quantity squared. Okay? So it just looks exactly like the 6 minus x, but instead of x, I have 1 plus h. Now, depending on the last algebra class, you may have done something like this before. You may not have. It's one of those topics that's usually covered, but it isn't always. So for some of you, this may be the first time you've seen this kind of a calculation. I hope not. But if it is, it's just going to take a little getting used to, okay? This, however, at this point, is stuff you've done for quite a while throughout your math in high school. So we're going to square 1 plus h, and that is not 1 squared plus h squared. How do I square 1 plus h? As a FOIL, exactly. So what you want to remember is that this is the same as having 6 minus 1 plus h times 1 plus h. If you don't need to write it out to remember or to think about it, that's fine. If you do, then write it. Space, I do, good. All right, so we're going to FOIL that out. So what is 1 plus h times 1 plus h? I'll distribute the negative in a minute. Exactly. So this is 1 plus 2h plus h squared. Okay. That's right. I'm right there now.
Can I ask you a question?
You bet.
Before we go any further?
Mm-hmm.
Back on there.
Yep.
I kind of on that 5. You had like a negative f of 1.
This one?
The second one, negative f of 1.
Uh-huh.
You had negative 5.
Right.
Is that just
Well, the negative is subtraction, so it's not really like a negative.
okay?
But where did the 5 come from? Do you remember?
From the plugging the 1 in, right?
Right. F of 1 is taking our function here and plugging in the number 1 for x.
Okay. And then with the second one.
Oh, you're saying that I've got it rewritten down here in the wrong spot. Yeah, I can fix. This is what Noah's telling me, which he's right. Let me fix that. was not written properly. You are correct. Okay, back to you, Chancellor. Was that your question? I didn't think so. But I'm glad we fixed it anyway. All right, what's your question now?
And then with the 6, where did the 6 come from? Is it
It's
still
in the formula.
So it wouldn't be the
This-
F times.
This whole expression came from here,
Okay.
right here. So the 6 is part of the formula. The x is this piece right here, but the x value right here is 1 plus h. So the 1 plus h is replacing the x value. Okay? All right, you guys ready to simplify the expression a little bit more? Yeah. Some of you have already started, I can tell. Okay, so I've got the limit as h goes to 0. 6 minus 1, that's 5. Right, I just did I'm distributing my negative through. And then I have minus 2h and minus h squared minus my 5 over h. Now what?
Subtract 5.
Yeah, this 5 and this 5 add to 0, right?
Subtract h.
And then we're going to factor in h out of the numerator. Everything, when I get to this point, everything in the numerator has to have an h in it. If it doesn't, there's an error in my work. Why does it have to have an h in it?
You can't factor it out.
Because I need it to cancel out with the factor in the denominator. Exactly. So I'm going to factor out an h, which is going to leave me with 2 negative 2, minus h over h, because I need those h's to reduce, or I'll never be able to plug in 0. So where I am right now says the limit as h goes to 0 of negative 2 minus h. What do you think's next? Yeah, now I can actually evaluate this, what happens in the case when h equals 0. I get a limit value of negative 2. And what in the world did I do all that limiting for? Well, I did it to find the slope. M equals negative 2. That is my slope. So back over on this one right now here, and I'll put it back over there. That's the negative 2 that goes there. Those are the 3 values I need to create a line. So now I have y minus 5 equals negative 2 times x minus 1. And we're going to solve it for y equals, because that's how we would be able to graph a line if we were working on it from our calculator point of view. So this is y minus 5 equals negative 2x plus 2. Add my 5. So this is y equals negative 2x plus 7. Now I want you to take your calculators out to look at something, okay? As soon as you get that written down, grab your calculator. In your calculator, I want you to put 2 equations. The first equation I want you to put is the original parabola that we started with, 6 minus x squared. So put that in y1. The second thing I want you to put in is I want you to put in this line that we just found as our answer, negative 2x plus 7. Okay.
What'd you say for y1?
In y1, you're going to put the function that we started with, which was 6 minus x squared. And in y2, you're going to put the line that we got as our answer, negative 2x plus 7. What this should look like is an upside-down parabola. That's what 6 minus x squared is. It's shifted up 6, so it's crossing the y-axis at 6. And it should look like a tangent line resting on it at the x value of what? What x value should this be touching our parabola at? Close.
X value?
Yeah, it is 1. I'm sorry. Not negative 1. I was thinking negative 1 from what we've done before. Yes, at 1, because it says a equal 1, right? So this should look, and I'm going to just draw you a sketch. It's not going to be anything close to perfect. But the basic image you should be seeing looks something like this. Are you getting an image more or less like this? Okay. Now this doesn't prove you did it right, but at least gives confirmation to you that it seems reasonable, right? If the image looks something like this, you knew you made a mistake. Then it doesn't even touch the curve, right? Or let's say, for instance, you got something that looked like this, and you knew the x value you were supposed to be touching out was the value of 1, or even like this, you'd know you made a mistake, because this should be touching at an x value of 1 because your equation had an x value of 1 that you're supposed to be working at. Does that make sense? So if you're creating the tangent line, you should be able to confirm to yourself that what you found is reasonable. All right. Let's take a look at another definition. It looks very similar to the one we just did. This is a definition for instantaneous velocity. If s of t represents the position of an object relative to a fixed location at a time t, and it's moving in a straight line, then instantaneous velocity, which means the velocity right now, not average, not I average 30 miles per hour driving from here to there. It's not an average. It's an instantaneous velocity, what's at right exactly right now, at the time t equal a, is given by v of a, that stands for velocity. Limit as h goes to 0. Get used to that. It's going to be there all the time now. We're going to have lots of limits as h goes to 0. Of s of a plus h minus s of a, because s was the original function right up here. The original function. Evaluate at the point A and the point A plus h slightly away from A. And we simplify the denominator so it simplifies exactly like the one did before when we were talking about the tangent lines, provided the limit exists. The word we use in our English, I want to say the word vernacular, our sort of common English language, is the word speed. Speed and velocity are almost the same thing. Speed is actually the absolute value of velocity. For instance, if I tell you that I'm going 50 miles per hour because I look at my speedometer and it says 50, that doesn't actually tell you whether I'm driving to Shawnee or away from Shawnee, right? If I were working with instantaneous velocity, one of those directions would be considered positive velocity, and the other one would be considered negative velocity. So it would give you more information. It would tell you the direction I'm heading as well as how fast I'm going. It's the only difference is that when we talk about velocity, we're also talking about moving in a specific direction. Okay? So we're going to do an example of one of these. And I'm going to do the problem in a slightly different way. Now, I want to take a look back. Is everybody getting this pretty close to written down? Okay, if you're not printing out notes, then that's a problem because you're going to have to be writing down more. It'll take you longer. Notice when I did this right here, I plugged in a equal to 1. I mean, I knew the a value was 1, and I plugged it in like right away. Now, you can do that, and it doesn't hurt, and it's nice and fine, and there's no problem. But sometimes you might want to know what happens when a equals 1, and a equals 2, and a equals 3. Well, I don't want to calculate this thing 3 times. Are you with me? So I'm going to show you another way you can do that generically so that you could evaluate it at multiple times instead of having to evaluate it every single time and doing 3 separate limits. So let me show you. What I'm going to show you looks a little bit different than the last one just because I want you to see that there's another option. So we're going to find the velocity at time A, and I'm going to leave it written at A in general because I want to evaluate this at A equal to 1 and A equal to 2, and I don't want to find the limit twice. I'm kind of lazy. You guys are too, right? If you can do something faster, you're going to, at least if you think to do it that way. So that's what we're going to do. We're going to do it in a quicker way. So we're going to leave this written in terms of A instead of being written in terms of A equal to 1 or A equal to 2. All right, so this is a limit as h goes to 0 of s of a plus h minus s of a over h. It's directly from that definition above. Directly. Looks exactly the same. The only thing you see different is, I don't even think you see anything different. You don't see the middle part. That's what you don't see. You don't see this middle part right here, right? You just see the first part and the last part. Okay. You have a function which is not done very well here. It should be called the function s of x so that they all have x's in it. So just make that alteration if it's not on your paper already. It should say x there. You have a function s of x, and it has the equation 2 over x plus 1, right? So what we want to find is we want to find s of not x, but a plus h. What that means is that I take my function, and where I had x, I now have a plus h, because that is my x value. So I end up having this look like the limit as h goes to 0 of 2 over a plus h, that's where the x was, plus 1. So I'm taking the function that's called s, which is 2 over x plus 1, and I'm rewriting it here. But instead of writing x into the function, I'm using the a plus h as my x value. So I have 2 over a plus h plus 1. It's just notation. It's just a replacement. That's all it is. The next replacement's even easier because it says that I'm going to take that s of x equation, 2 over x plus 1, and instead of using x, I'm going to be using just a. So this is going to be written as 2 over a plus 1. Just a change of variable. That's all I'm doing. Changing out the variable x for something else. They happen to be letters right now instead of numbers. Now, the goal is still the same. That h in the denominator has to go away, or I can't plug in 0, right? But this is a different kind of equation. It's got a denominator. Like, I've got 3 denominators I'm looking at here, right? I have this little denominator, a plus h plus 1. I have this little denominator, a plus 1. And then I've got the whole thing's denominator, h. That's a mess. Agreed? How in the world do we add or subtract fractions when they have different denominators? You need a common denominator, so that's our next step. Ignore the over h part for now. We're going to deal with it in a minute. But right now, our goal is to add these 2 fractions, or actually subtract these 2 fractions from one another. They need a common denominator. Now, these 2 denominators don't have any factors in common. They have terms in common. Remember, terms are things that are separated by addition and subtraction. They definitely have terms in common. They both have an a, they both have a 1. But they don't have any factors. That's multiplication in common. I can't factor them and match anything up. So that means that the only way I'm going to get a common denominator is if I simply multiply those 2 denominators that are already there together. So the first fraction will be multiplied by a plus 1 over a plus 1. The second fraction will be multiplied by a plus h plus 1 over a plus h plus 1. It's not as ugly as it looks. So just bear with me for a couple more steps. Because things go away, which is the whole point. All right, things are going to go away. Now, the numerators we really are going to multiply out. So I'm really going to multiply 2a, or 2 times a plus 1 to get 2a plus 2. And then this piece right here is actually a negative 2. So I'm going to multiply negative 2 through the other set of parentheses. So I'm going to get negative 2a, negative 2h, and negative 2. All of this is over the new common denominator, which is called a plus h plus 1 times a plus 1. I do not need to multiply that out. Don't. It's going to be work that you don't need to do. Okay? And then all of that will be divided by h. But I'm about to shortcut that too. Division, we'll use a number here for just a second. Let's say that you wanted to divide by the number 3. How else could you think of division by 3? Multiplication by 1/3, right? So this is division by h. Agreed? So instead of thinking of it as division by h, I'm going to think about it as multiplication by 1 over h. Yes, Tammy?
Wouldn't it be, like, the denominator, would it be squared? Because you're multiplying a plus h plus 1 times?
I'm going to let you answer that question for me. If I add 2 over 4 plus 3 over 4, does it become 5 over 4 squared? No. And the same thing's happening here, but with a different denominator. I mean, they look different, right? This denominator and this denominator match now, so they are my new common denominator. Yeah. When you're in doubt about some fraction things like that, turning it into numbers often helps you to remember how the process works. Yes, Luke?
Why does your denominator now have an a plus 1?
It had an a plus 1 in it to begin with. Right here.
Where?
Do you see that?
Then, oh, I see that one, but like on the bottom.
Uh-huh.
Did you just,
They both have a plus 1. This denominator is a plus 1, h plus 1 times a plus 1. This denominator is a plus 1 times a plus h plus 1. So my denominator is a plus h plus 1 times a plus 1 because those are the two original denominators I had. This h right here
Oh, you just moved the
is
h.
now over here.
So, I mean, it'd be basically the same thing, just saying that, like, if you just wrote one giant line, put an H underneath all that.
It would, but eventually you got to pull that h up or it's not going to simplify like you want it to. Yes. I just did it in that step.
Gotcha.
Yeah. All right, any other questions before we keep going? Okay, there's things in that numerator that simplify, aren't there? Somebody tell me one of them. 2a. All right. Somebody who didn't just say 2a, tell me another one. 2. So what is actually left in the numerator? Negative 2h. All right, so let me simplify what we've got. And this is not uncommon. That's the whole point. Things are going to fall out. I have negative 2h in the numerator. I've got a plus h plus 1 times a plus 1 times h. Right? When I multiply fractions, I multiply numerators, I multiply denominators. So the h can actually be written in the denominator. And that's a good thing, because now what happens? Yes, I do. My h's will reduce now.
Can you just cancel it in the step before that?
Yes, you can. I just don't want, oops, I'm running out of space. I just didn't want to cancel so much that people lost it. Yes. All right, so I can't do what I was wanting to do. That's fine. All right, so this gives me the limit as h goes to 0 of negative 2 over a plus h plus 1 times a plus 1. Oops. I need to go to a new screen, so let me find a screen for us. Okay, this is v of a. I'm not quite done yet. Now what do I need to do?
Plug it in, all your stuff.
Plug in something before then.
H, O, 0 for H.
Yeah, plug in 0 for h, right? I've gotten rid of the h that was causing problems. The h that's in here now, if I put a 0 in there for h, it's not going to cause any problems. So I'm able to actually let the h value here be 0, which will give me,
You no longer have to write them in front of it.
right, as soon as you plug in 0 for h, you do not need the limit as h approaches 0 anymore because you've allowed it to be 0. So this gives me negative 2 over, actually, a plus 1 squared. If you want to write it as a plus 1 times a plus 1, that's fine. But I've got negative 2 on top, and I've got a plus 1 and a plus 1 on bottom. So we've calculated the slope. This doesn't look like a number, though, and the reason it doesn't look like a number is because we did it for arbitrarily any value for a. But we were told we wanted to find it specifically for an a value of what? 1 and an a value of 2. I've calculated the limit one time, and now I can find 2 slopes. I just cut your workload in half. I mean, right? This is a really good thing. So now I just plug in each of those particular values one at a time. For a, oops, I didn't write here 2. All right, so what's the first one? Negative 2 over what? Over 1? 4, right? Okay. I have 1 plus 1, and then square it, so I've got 4. So this first value is negative 1/2. So the first slope, or velocity, in this case value I have is negative 1/2. The second velocity is negative 2 over what? 9. That one doesn't even reduce, so it's just negative 2 over 9. So this step at the end is quick and easy, simple stuff. You're just evaluating. It's the steps before that are a little more complicated because you did it in general to avoid having to do it twice. That's why.
These are very involved.
They are very involved, and you're going to be doing a lot of them. I wouldn't do any of them until after Thursday if I were you. I'd just let this set aside and not touch it until after Thursday. That's my suggestion. Okay? Thursday's your test. Focus on preparing for that. And then you've got 5 days over the weekend. At any point in those 5 days, you can come back to this. You can listen to the video again too, right? Because it'll be out there for you. All right, let me show you a couple other things here. These you'll like better, in part because there's pictures involved, I know. This one says to sketch a plausible tangent line to the points A, B, C, D, and then list the points in the order of increasing slope. Now you actually have points on your graph, so I'm going to put mine in so that I have the same thing you do. See how thick that is. Whoop, that's too big. Yours doesn't? Mine does. Okay, just put them in fairly close to where I'm going with mine. Let's go with that. We'll do it all together then, since nobody has them. Oh, I remember. When I was creating this, I think that I had issues with Word wanting to draw the dots on there for me. I think that's why. All right, so these are sketches. My suggestion when you're working with these is to have some kind of a straight edge. Now, that means you might want a ruler, but in all honesty, your ID card or your license will work just fine. So grab out something that's got a hard straight edge for you. Everybody has something surely with you. If not, you can use the edge of your calculator, the edge of your textbook, or a sheet of paper or something like that. But
Dr.
ID cards work nice. Yes?
Good question for you. So in the last problem there, we weren't solving for the equation of the
No.
tangent. We were just finding the slope,
Well, we were finding velocity,
which is the derivative.
which is the same as the derivative. Yes, we're finding the velocity at a specific point in time. So the speed of something, how something's moving. Yes, you're exactly right. We were not finding a line on that one. All right, so here's that image. We're going to find tangent lines. So in general, how you find a tangent line when you're sketching, because that's what we're asked to do here, is to just sketch something. And I sort of drew things before without sort of arguing to you why I was doing what I was doing. So you're going to take your straight edge, and we're going to pretend like my straight edge, you know what? I'll use the binder that I'm working with. Is my binder. Oh, I've got a ruler. I'm going to use a ruler. All right? So you're going to take your straight edge, and you're going to line it up on one side, and it's usually the side where it's sort of bowing outward. Like this is sort of bowing one direction, and you're going to be on the other side of it. And you're lining it up so that it looks like it's touching at that point and only that point. This is not going to be perfect. So I'm drawing mine like this. Yours might look a little steeper and look more like that. But they're going to be awfully close. If you draw a line that cuts through the graph, that's not okay, obviously. So this is going to look something like this. So my first line, I lost my stylus. Oh, on the floor. All right, my first line looks something like, and I'll draw it in red to just distinguish, something like that. Yours look something like that?
Yep.
Excellent. All right, the point B should look like it's at the very top of that peak. That's how I drew it on purpose. Okay, so make sure your point B looks like it's at the top of that peak. Here's the problem with the point being at the top of the peak. If I draw it like this, it looks closer to the left-hand side. And if I draw it like this, it looks closer to the right-hand side. How do you think I might have to draw that one? It's right on the top. It's a horizontal line through the point B. That's the best way that I can get as close as possible to both sides of this curve. So on the point at B, my tangent line looks something like this. It's not perfect, but it's close. Now the point at C is drawn in such a way that in order to get close to the left-hand side and the right-hand side, we're actually going to have to do something that looks like we're cutting through the graph. And we are, but we're doing it in such a way that it's very, very close to both sides. That only happens at specific points, and we'll talk about later what those points are called. I'll give you the name right now, but we'll talk more about them toward the end of the semester. They're called inflection points. And if those of you who've had some calculus before might remember, those are points where we talk about something changing concavity. I'm not probably going to be able to draw this as well as I'd like. Oh, that's not too bad.
basically just draw your line with the black line.
Hmm?
So basically just drawing your line with the black line.
Yes, but if you need it, you need to extend it long enough across that so that it doesn't keep looking like the curve itself. Right? You should extend the line.
Are you going through that last one?
This one actually looks like it goes through, right? Because it's on the top side of the curve above, and it's on the bottom side of the curve below.
So are you trying to match it up with the points or dots?
You're-
Trying to match it up with.
You have to go through the dot, okay, whatever the point is you're looking at, the dot that we've drawn on the screen. And the idea is that if you zoomed in close enough on your calculator around that point, it's going to look very linear, very much like a line. So it's going to look like the line you're drawing. In some cases, and they are rare, this is one of them, it actually cuts through the graph.
So it doesn't matter like that point right there with B. It doesn't have to cross the B.
No, it's not actually crossing B anyway. It's crossing the letter B, but that's not the point B.
Just points are actually related.
Just one.
Yeah, these points are not related to each other in any way, shape, or form. They're just all drawn on the picture together.
If that like crosses both sides pretty much,
Mhm.
why could you just go like that?
Okay, so let me draw what she's saying. Why couldn't I do, it's a good question. Why couldn't I do this? Why is that not a tangent line? I mean, it cuts through the graph, and the last one cut through the graph as well. Right, Chancellor? So what's wrong with that? Any thoughts on why that's not what we want and the other one is?
It's not matching the slope at that point.
It's not close to the slope of the curve at that point. Our goal is to be as close as possible to the slope of the curve at that point. So we're trying to get the image that we're drawing to be very, very close to what the image looked like, but straight instead of curved. Good descriptions. All right, one more. Point D. This point D, I put this one in here on purpose because I want you to see that it doesn't matter that the graph's always above or always below or cuts through. This one's completely below the line, below the curve, right? My line is below my curve, actually. It's on the bottom side of the curve instead of being on the top side of the curve. So over here at the point A, my slope line is actually on top of my curve, whereas over here on point D, it's actually on the bottom of the curve. I want to extend one of these graphs. I'm going to delete what's on this screen. I want to show you one other thing, okay? Does everybody have these drawn in pretty close on your papers? Okay, I want to show you one other thing about this that's interesting. I want to take, and it doesn't matter which one I take because they all actually do it, but we'll just take the point at B that I did and draw that line again, in theory. That's pretty good. If you extend this line, this particular line out far enough, it will cross the curve again, right? Because this curve actually turns back upwards. Parabola didn't do that, but this curve does. That's not a problem. That's not a problem at all. The issue about not crossing the curve again or something like that has to do with the close values. So in an area nearby B, it's not going through two different values. At least if I drew it well, it didn't. Okay, so the fact that it crossed it out again somewhere out in space is not an issue at all. Okay, so I don't want you to think, oh my goodness, it crossed it, this can't be the tangent line. Well, it is. Just tangent line has to do with a nearby value being something. Okay. All right. A couple other things that you should be aware of. There are 3 locations where tangent lines do not exist. Discontinuities is the first one. Okay, there are 3 types of discontinuities. So this is review about your test right now. What kinds of things cause discontinuities in a graph?
Holes.
Holes,
Asymptotes.
asymptotes,
Jumps.
excellent, and jumps. So if you're talking about a specific point on the curve where there's a hole, a specific x value on the curve where there is an asymptote, or a specific x value on your curve where there is a place where your graph is jumping, you do not have a tangent line there. Okay, you have to actually have a function value that has not got any discontinuities at that particular point in order to have a tangent value, tangent line. Sharp turns is another one. So what do I mean by sharp turns? Well, sharp turn means that you've taken the graph and you've done something where it changes something else. Like this would be a sharp turn. That point right there. The slope was doing one thing and then immediately it changes and it does something completely different. Right? The slope from one side was this increasing, maybe about about m equal 1 kind of a slope. And the slope over here is now all of a sudden negative. And it wouldn't necessarily even have to change from positive to negative. It could do something like this even. It isn't changing from positive to negative, but it is definitely changing from positive to something less positive instantaneously. Right there, right then at that point. If it's got a sharp turn, it does not have a tangent line there. And the reason is because the tangent lines, if you created it from either side, wouldn't match. And the last one is vertical tangent lines. You do not see this one happen very often, but you need to be aware that it is an example of one. If your curve does something like this, where it is flat out vertical, right here at this point, it has a tangent line. The line's vertical. But the problem is that what happens when you talk about slopes of vertical lines? Do you remember? They're undefined. This slope, you might have heard the language used is that it has a no slope, which is terrible language. It has undefined slope because it is a vertical line. So when we find tangent lines, we're not going to be able to find a tangent line slope. So this probably should have said where tangent lines slopes don't exist would be probably a better description.
So will we be like writing like does not exist on some
Yes,
columns?
you could.
Okay.
These cases I bring up because you need to be aware of them. In reality, they don't happen very often. The only way that you get poles and asymptotes is if you have functions that are rational functions, right? Numerator, denominator. That's very specific. The only way that you get a jump in the graph is if you have a piecewise function. How often do you see piecewise functions? Not very often. Okay? Occasionally you're going to work with them, but it's not going to be the regular or the norm. All right? Sharp turns. Sharp turns are only going to happen with piecewise functions. Okay? Again, not very often. Vertical tangent lines are very difficult to find. There's probably 2 in your entire textbook or something. I mean, like, seriously, it's not going to happen. All right? If it happens, it's going to be a very rare situation. Most of the time, you're going to be dealing with the functions like we dealt with already today. Functions where you have a rational function, 2 over x plus 1, but they're not asking about what happens at x equal negative 1, right? They're not. That would be either a whole or an asymptote, and this one would be an asymptote. Or you're dealing with something that's even friendlier, like this one. It's quadratic. It's parabola. Parabolas are very friendly for working with on these. Okay? Any other questions on this?
So,
Okay, one at a time. Yes, go ahead.
sorry.
It's okay.
We could have just derived and been a lot simpler, but this is basically finding the slope in terms of limits instead of finding in terms of
Of what? In terms of derivatives?
Yeah.
We're getting there.
Yeah.
Those of you who've had calculus before know the end game we're approaching. And it's wonderful. It's so much simpler than the limits, right? Okay. Those of you who have done that before are going, yes, I get that. And the others of you have not. Who hasn't had calculus before? Okay. So all those people who just raised your hands, you're actually at an advantage right now. You are, because you don't know what's coming up exactly yet. All right? Those of you who've had calculus before, when it asks you to find slopes of tangent lines, this is what it's asking you to do. We're only going to do it for 1 or 2 sections. Okay? I promise. It's not going to be that long. It's not going to be that painful. Yeah, 1 section, 2.1. This is the only homework you're going to do it like this for.
It's going to be painful.
It's not even that many problems. What do I have on there? Like 8 problems? You can do it, I'm quite sure.
On like